Well, thanks to the organizers for asking me to talk about this. It's a great subject. I was struck in Don's talk about the timescales he mentioned. It's been 18 years, I guess, since Juan's paper. Well, it's been the same time since the paper laying out how to use bead mode measurements to measure tensor modes in the CMB. And since then, there's been an amazing experimental progress and some theory that's related, including quantum gravity. And this is one of those rare occasions when we can discuss observations. I don't just mean observables, but I mean actual observations in connection with quantum gravity with a straight face. And so even though this stuff is, somewhat mature now, despite being relatively recent, it's a good thing to cover in the program. So there are a lot of wonderful collaborators that I've had on this topic, as well as many, many works by others. It's really a large field. And there are even many, many reviews. Cliff gave a nice overview at a recent Planck meeting. Liam McAllister and Dan Bauman put out a book on the subject. I've written numerous reviews. Those are recent ones. So you can find a lot more on the web if you want. Okay, but I am going to try and make this kind of an overview / update of the subject because I think people are pretty well aware of it. So I'll start with a very brief review of the connection to quantum gravity, a brief update on the data, including not just the recent releases, but the forecasts that the experimentalists are making. They've been doing incredible things just in the past few months to move things forward. Then I'm going to make a theoretically very trivial, but I think important argument that Planck et al. Have discovered a new parameter in cosmology, and that this is good for the connection to UV physics. And then I'll discuss a couple of things going on in theory, improving the theory constraints on this subject. In particular, lately, some folks on the archive have been debating a possible connection between the so-called weak gravity conjecture and certain types of axion inflation, a kind of multi-field version of natural inflation. So I'll try and cover that, even though it's not something I'm working on, as well as systematics of the sort of generic mechanism for large field that we have in string theory. And then I'll finish with some fun phenomenological opportunities with the Planck data, if we get there. So also, I can scale this to whatever topics people are most interested in. I'm sure I'm going to bore most people with this, but let me just, for completeness, say the reason that this subject is connected to quantum gravity follows from a nice, simple two-line argument. Take the number of e-foldings in inflation, integrating dA over A being the scale factor, apply the chain rule several times, and you obtain the famous relation between the range of field excursion of the inflaton phi during inflation in Planck units and the tensor to scalar ratio R. Here I just use the single field slow roll expressions for simplicity. You can include the sound speed if you want. And there's an assumption here of nothing really funny happening, no very strong variation, so that I pulled these factors out of the integral, as you can see. Also, this assumes there are no exotic sources that account for any tensor modes that are seen. Okay, so there's this relationship. It's incredibly convenient because the apparently detectable value of R of 0.01 is of order this really interesting threshold of a Planck range and field. So something actually observable is highly UV sensitive, simply because if you think about an arbitrary potential energy, allowing for a series of higher dimension operators suppressed by the Planck scale, which in itself is kind of conservative. All sorts of lower scales could enter into this, and generally do in string theory. These all have, an infinite sequence of these are important in an inflation scenario in which the field goes that far. Although you can make a symmetry argument from the bottom up, it's a radiatively stable possibility for this to happen from the bottom up. it still makes, a big assumption, at least about the symmetry structure of quantum gravity, to do that. And so I think it's a standard view in the field that this is honestly sensitive to quantum gravity, at least to its symmetry structure. And for me, I'm going to take string theory as the most serious candidate for quantum gravity and work with that. One thing that I've been emphasizing all along throughout the roller coaster of the past year is that, which is logically obvious, inflation is not the thing that's at stake here. What is at stake instead, and I think I can say that here among friends without any trouble, is the strong connection to quantum gravity that this represents. And one nice thing is that this is not, on the other hand, the most exotic possibility for inflation. There's a real sense in which the simplest mechanisms do this as well. So that's kind of a nice coincidence. Okay, so very briefly, the theme of this program is UVIR. This is, I think I'm really supposed to represent the UV side of things. We've had tons of talks on the IR issues in inflation so far. But I want to just mention briefly that the legacy that this has had so far, until we know more from the data, is that it's actually fed in a surprising way into the IR, into the low energy effective field theory treatment of the subject. A serious, complete systematic study of non-Gaussianity at the single field level was highly informed by mechanisms that popped out of string theory. Also covering the cases involving discrete shift symmetry, dissipative processes, and exotic sources like cosmic strings and bubbles and so on have been very much informed by the top-down view. So whatever else is true, at least it has done some good. Now, the big picture, of course, from the latest Planck release is that lambda CDM is doing extremely well. So this is their TT power spectrum, and it's reproduced independently in polarization. So the curve is the lambda CDM curve. For inflationary physics, it boils down what could have been an entire function to two numbers. And that in itself, to me, is a function's worth of evidence for the inflationary paradigm, or for any alternative that would accomplish that. But I don't think we have a credible, a theoretically understood alternative. So anyway, as such, as far as inflation goes, this is why I say inflation is not the thing at stake.
Sorry, Eva?
Yeah.
You say 2 parameters. I mean, usually I hear that there's like 6 parameters.
There are 6 parameters. I said as far as inflation goes.
Okay.
Yeah. So there's 6 parameters. It's highly over-constrained and yet boils down to 6 parameters. So it's the same, even if you think more broadly, the same point holds, that it's incredibly beautiful. Whether or not new physics, so to speak, is discovered next. Such possibilities are still very much alive in the form of tensor modes, further structure in the power spectrum, and also higher point correlators that we've heard a bit about at this workshop. But, some random, wacky theory of the early universe will probably be dead on arrival in this, given the beauty of this data. Okay, so there's been a lot said about R. Here's the current status of it based on the joint analysis between the BICEP Keck teams and Planck. So this is their posterior on R. They discovered dust with good significance. And I used to go around asking them my reverse psychology question. So do you understand it well enough that you could make it? And the answer is yes, they can. Of course, I mean polarization from dust. So the
question about the dust, actually.
Yeah.
Is the signal they saw from the CMB scattering off the dust, or is it from some other source of radiation?
It's another thing. It's starlight. Dust absorbs starlight and then emits as a sort of thermal.
Right. So the emission from the dust came from whatever
it absorbed. Whatever it absorbed. And I'll say a little bit more about this. I mean, not much, but. But they treat it as an empirical thing, really. It's not that there's a theory that predicts, as you know, the theories were kind of misleading. Okay, so here's the posterior currently. 0 is perfectly consistent. The peak is at R of 0.05 or so. You should not. One should definitely realize that this remains an enormous advance experimentally. treated as a bound, it's competitive with an indirect one from just the temperature data, but now directly determined. And I'll say a little bit more about this later, but all the data together has reduced the viable region in the plane of the tilt of the spectrum NS and R by a whopping 29% just from this. And more importantly, the experiments are really, they've established the experimental methods, and they all say they're going to get there. So just for fun, here's another slide about the joint analysis. They did various alternate analyses. It doesn't do too much to the likelihood, so it's pretty robust. George sort of points out that if you relax the prior on how the dust scales from higher frequencies to lower frequencies, it pulls R out a little bit to 0.06 or something. But it's basically robust. So a huge amount of steps have been taken just in this past winter. For one thing, the Keck array, which is 5 bicep 2s, now is running at several frequencies. As you can see, they put 220 gigahertz receivers in just recently, or I think sometime last fall, and that gives them their own dust channel, in addition to 95s and 150s. Bicep 3, meanwhile, just deployed this past winter. This is Zish Ahmed. He's one of the leaders of that project, and it's running successfully. I'll say more about other experiments. Spider flew, and various others are progressing. So their projections for what's going to happen next, just in this lineage of experiments, is the following. So I showed you the likelihood that is current with what they have already collected and are analyzing. If it sharpens around 0, it's this green line. If it sharpens around where it is, it's this purple line. So that's how much what they have could improve things according to their forecasts. And the bottom is how much it will improve with what they're collecting now with these receivers that I just mentioned. So again, the purple is sharpening where it is. The green is around 0, and of course, no one would be surprised if it lands anywhere between 0 and 0.1 or so.
It could be a 2 sigma detection of non-zero R.
Yeah, so the probability to exceed is 0.6%. So this means if they just had a foreground-only true sky and asked how likely would it be statistically for this to appear anyway, just as a statistical fluctuation, the probability would be 0.6% according to. So that's how to read these curves. Right now, I think the statement is it's 8%. So that would get it down to 0.6% would be the statement, I guess. But one should keep in mind that if it gets to that, then there will be a further step of scrutinizing the residual and making sure that we understand what's in there. So, okay, so it's really the experiment is moving faster than the theory. I have to say it's pretty cool. I shouldn't shortchange other projects. Spider is a balloon that flew this past January, also with the sort of 100, 150 frequencies so far, and there will be another flight with more. I recommend their YouTube videos. So they put a GoPro camera on it, and you can see pictures of the South Pole. ACT is going to upgrade to go after R with multiple frequencies. CMB stage 4 in the U.S. generally is going to ramp up the number of detectors. And there's a lot of interest in going to space. I think Japan is first to get things approved. So anyway, the experimental community, despite all this complication that we've heard about, seems just universally optimistic about determining R within this range. Yeah.
It's probably an unfair question, but is the reason that they only do single frequencies just power?
Well, I don't really want to speak for them, but they integrated deep in one frequency to collect as much data as they could. If they had seen nothing, it would have been the most direct way to get it bound.
I assume they did it because they got something out of it. So is it again?
Well, you're limited in frequencies also, they're limited by when and how many detectors are actually fabricated and stuff like that.
Right.
You know, there's a step-by-step procedure, and they're well into it. And,
Right.
You know,
but it's that if I set it a single frequency, I can just put all the detectors on that, and I just get a better, better signal.
That's right. I mean, I think one way to say it would be if they had seen nothing, it would have been the quickest way to get to a bound.
Right. Sure.
Instead, they saw something, and then we have to understand what it is. Okay, so now let me make my theoretically trivial argument that a new cosmological parameter has been discovered, which is simply that if you put everything together, this famous m squared phi squared model of inflation is now, in their words, strongly disfavored. Okay, it's not anywhere near I think it's like 3 sigma off. Now, this model has the property that with only this parameter m and where you start in field space, it has everything that we need. It has the CMB that is observed plus an exit from inflation, just built in. But to the extent that it is excluded now, conversely, that means we need at least one more parameter to describe all the physics that we know.
Could you please explain what's behind the fact that it's strongly disfavored?
Oh, these dots are the m squared phi. This is m squared phi
But
squared.
I mean, not just looking at the graph, but what physics is implied by m squared phi squared that's not consistent with the data?
It's predictions for the tilt and more importantly, the tensor to scalar ratio. So it sits here. So okay.
So it's too
I'm sorry.
much.
I should have said what this is. This is the plot of the viable region observationally for the tilt of the scalar spectrum and the tensor to scalar ratio. And this m squared phi squared model, just at the single field level, makes this prediction that uncertainty has to do with reheating.
It's a fairly constrained model. You have one parameter, and you're trying to hit both the power and scalar fluctuations as well as the number of endpoints.
So if we grant inflation, I'm saying this is the origin of parameter space, and now we've moved away from the origin of parameter space. So, in my humble opinion, they discovered a parameter.
It's too much tensor amplitude.
Yeah,
That's what you're
yeah.
pointing to here. And the reason in terms of the shape of the curve, I mean, it would be good if you could just orient.
Well, it's because the field
Not everybody's
range.
an expert here. So what is it about the shape of the potential that's causing the problem here that some other potential wouldn't cause?
Okay, well, that's sort of where I was going to go. One could say it in two ways. I already said in terms of the field range, you're probably heard more about the relation between the tensor modes and the scale of inflation, right? So the 2-point function of the tensor perturbations goes like Hubble squared. That's all that determines it, up to smaller effects of slow variations. And so if you compare the phi squared model to something that is flatter than it, lower energy than it, it'll produce more tensors, and that's more or less what's happening here. I mean, I don't mean to make this sound mysterious at all. So concretely, you take this model, you insist that you have 60 E-folds. You go 60 E-folds back. That tells you where you start the field. And then, the first 10 you see in the CMB.
I think perhaps what he wants to know is it's a relation between how steep the potential is and how big it is.
Well, I did the Lyth relation earlier.
I mean, basically, you could say that the potential is too steep, so the field rolls too fast, and that gives more gravitational waves.
Well, but it really is just the energy it contains. Okay, yes.
If we assume it is ruled out, does it say something about the landscape it's going through?
Well, I think it does, and I'm not just saying this post facto. We said this before, for what it's worth. I claim this is good from the UV for the following really pedestrian reason, which is if you take, the inflaton and you couple it to other fields, even ones that are heavier than Hubble, those can and do adjust to the inflationary potential energy, and they do it in an energetically favorable way. And when that, remains consistent with inflation, meaning it doesn't just destabilize the whole thing, it leads to a flatter potential simply because that's more energetically favorable. So that goes in this direction.
Thanks. Could a phi to the fourth be okay?
No, phi to the, so, okay, good. So I'm sorry. Phi to the p goes up in this direction as you increase p. So lower p is better. And just to anticipate, these lower p's are what we found in string theory in the same class of.
What is the model at the bottom there? It's like kind of an orange color right at the bottom here.
Well, that might be the Starbinski, where you have he originally formulated inflation not in terms of a scalar field of its equivalent, but in terms of an r plus an r squared. You have to ask what about the corrections. That's again viable. It's hilarious because a certain fraction of the community bounces around between m squared, phi squared, and that. I think it's probably somewhere in the middle. But, and by the way, okay, we should take this with a grain of salt. It could bounce back up for all I know. Okay, so this is just. I do apologize for the theoretical triviality of this talk, but that's kind of the point. It's kind of, to me, it's amazing how much of structure formation boils down to the very simple ideas. Okay, so here's a field theory toy model for what I just said about heavy fields. It's just what I said in words. Here I'm taking a light field, which is the candidate inflaton, coupled to a field phi heavy, which by itself wants to be massive, and wants to be sitting at some 0.50, which if you just stuck it there would give you a phi squared theory, but instead it adjusts. And in fact, in this toy model, it becomes just absolutely flat. In more realistic top-down examples that we have in string theory, this effect takes us from potentials of the form phi to the n for some integer, so around some appropriate origin and field space, things are analytic, and this back reaction effect flattens the potential, just for pretty obvious reasons. Okay. I don't want to imply at all that that's the only thing that happens in string theory. In fact, some of the classic models, this one, the roulette model, and Cliff has done interesting work on this fiber model, which I guess is kind of the closest type of thing to the Starbinski that we have. There are others that give interactions that slow down the field and hence non-Gaussian corrections. And this is probably an incomplete list of things that people have happened upon. So string theory gives a very non-informative prior on R overall, however, and on all the other observables. However, the different mechanisms are really very, very different. So it's like in quantum field theory as far as I'm concerned. When we do quantum field theory modeling of different systems from particle physics to condensed matter, we don't worry that there isn't an overarching prediction of quantum field theory. I mean, there are some principles there, but to get started making predictions, you have to describe the content of the theory that is appropriate to the given system. And that's how I view this. It's just that in inflationary cosmology, to do it properly, strictly speaking, one needs to account for these Planck-suppressed operators. That's even true at the small field level. It's not in infinite sensitivity, but it's still a sensitivity. You make order 1 corrections to the slow roll parameters. You ruin inflation if you write down a random correction that's Planck suppressed, even in a small field. Inflation, so those kind of require an accidental 1% cancellation.
This is just because the scalar makes a big transition for its range?
I'm just saying, so an example of such an operator is take the potential itself, multiply it by phi minus the point you are on the potential squared over m Planck squared, compute the change in eta, it's 1. So if you, any model of inflation is making implicit assumptions about those terms.
Eva, but if you allow nominal coupling, then in the Einstein frame things will look very different. So it's kind of
you can always go to the Einstein frame, and that's where I'm working. That doesn't change what I said. In fact, that's the frame in which it's clearest.
If I allow in Georgian frame to add these kind of operators, they will affect what happens in Einstein frame. So then you might get flatness, even though you.
So you can, add. I really did not mean to imply this is the only such parameter that could be added. It's just what I say here in a model independent way is that we need some other parameter. It could be many things. It could appear in a kinetic term, etc. That's a separate point from the other point that we were just talking about. That just go to the Einstein frame. If you're doing slow roll inflation, it's sensitive to Planck suppressed operators. There's nothing subtle about that, I don't think. Sorry, was there another question?
I was going to are you going to talk about the problems with that Stabilization model that's right in the middle of the probability region?
I'm not going to. I had an interesting discussion with Stabilization in Paris, and I don't want to misquote anybody, but I think he has his own view of the UV completion. It's a little more like the it sounded a bit to me like the asymptotic safety kind of idea. But I don't want to put those words in his mouth. The issue you would have with that, as originally written down, is that it, uses two of what one normally would think would be an infinite sequence of higher curvature.
Right. But I've seen people react to that problem by invoking supersymmetry, and I don't know what the result of all that is, but embedding that in a supersymmetric situation.
Supersymmetry doesn't change what we were just talking about. Again, just take any model you want. Add to it the operator. Should I just write it down? I really am afraid I'm confusing some people and boring everyone else, but just this operator, it's a dimension 6 Planck suppressed operator. You have 5 times it. This will change the slow roll parameter eta, which is the second derivative of the potential appropriately normalized. So it'll basically change, h double dot over h cubed in order 1, when in fact for inflation to work, this thing has to be of order 1% or so. That doesn't mean that you can take the data and turn it around and determine much about quantum gravity. You really can't. There are not that many parameters to use to do that, but that doesn't conflict with the basic statement that we read. Yeah.
Yeah, I think one way of saying something about the Stabilization model is that the higher derivative terms are equally important as the lower derivative terms. And so it's not one of those solutions where there are small corrections to low energy, low derivative solutions, but it's a significant deviation. It's kind of generally enlarging your set of solutions by adding higher derivatives. And this can only work if there's a kind of universality when you keep on adding higher terms and all that.
Well, I think that might be what Starbitsky would want to say. I'm not sure. Again, Cliff should comment on this when it comes to the other frame one uses to describe this, just in terms of a scalar field where it involves some exponential terms in the potential. I think even there.
Should probably.
At face value, it's true that if you just had a series in R and you had the same scale everywhere, then if you balance the R squared against the R, then you wonder what happened to the R cubed and everybody else. And they would agree with that, but they make, so I think Starbitsky's point of view is that you have, for some reason, the R squared term is if everybody was suppressed by the Planck scale, the R squared term is for some reason bigger than you generically would have thought. And so then he's going to balance the R squared with the R, but he'll say that and it's true that if you go to the solution, then if you assume that all the other terms are down by the power of the Planck scale, then they are small compared with the terms that he was.
That's right. Yes.
But I think he doesn't even want to make that assumption.
Well, then the question is, is there any UV physics that would give you that pattern?
Right.
And I think at that point he'll say no, but his hope is that there will be some asymptotically safe.
Yeah. Okay. Yeah, that's the same. Yeah. He certainly has every right to his opinion. For sure. It's not really in the center right now in R, but it could end up there. We'll see.
Cliff interpreted this same data, not to say we need another parameter, but that we should think about exponential potentials, which still have one parameter, I think.
Yeah, I love those potentials, I have to say.
I don't think they have. I think they must have more parameters, though, right?
No, I think if you write an exponential potential, just declare that the potential is an exponential. There's one parameter.
No. If you just have literally, no constant term or anything else, just an exponential, that's ruled out. That's way.
Constant plus the exponential.
Okay, so I guess you do have one more.
In fact, that I called the zombie scenario because it was temporarily revived by bicep. It cut up through the but now it's dead again. But okay, it is fair to say that all these things survive despite the 29% cut. And okay, there's more. But we're at a crossroads really in a number of these directions. Okay, so I don't know how much to do of the background theory, but let me back up and just say a few things. So just very, very generally, string theory as a theory of quantum gravity starts in higher dimensions, reduces to 4 along some compact directions. There are many, many scalar fields, including the interaction strength of the string, the sizes, and so on. And we try to understand the low energy theory that we get as a result of all these contributions, and work near weakly curved solutions. The potential has the structure classically of a bunch of terms like this. They are exponential in the dilaton and the radion, the canonically normalized radion fields, and they have a direct dependence on axions, which I'll come back to. There are all sorts of contributions, including defects like orientifolds, warping, say gravitational redshift, quantum effects, non-perturbative effects that come into various scenarios for stabilizing them. Axions I'll focus on, not because that's the only possibility, as I tried to emphasize, but it's a reasonable one to work through quite carefully. There are lots of axions. If you like the supersymmetric regimes of string theory, that is to say starting in d equals 10, they're sort of half the fields. Each multiplet has one sort of real component and one angle-like component. If you work more generally in string theory, these fields just completely dominate the spectrum. There are an exponential number of them as a function of dimensionality because Ramon fields are spinors times spinors. So they really exponentially dominate the spectrum of string theory as a whole. And even in the low-energy SUSY context, they're sort of half the field, so we should pay attention to them. They have some symmetry protection properties. It's a bit subtle because they do back-react on moduli. There are no global symmetries, but still there's a certain sense in which symmetry helps protect their dynamics. This has been an interesting story for quite a while. Tom and others emphasized somewhat early on in this subject that the single axion period is sub-Planckian. In the multi-field version...
Can I just say, we never claimed the number there was 1.
I know. Have you gotten pushback on this from someone?
No, it's just that people cite that paper as if we said the number was 1, and we just sort of said, F much bigger than M Planck doesn't seem to occur. Okay, fair point. Actually, it does seem to occur if you allow multiple fields, even before you include the monodromy effect. But that is the subject of this recent story with the weak gravity conjecture that I want to get to. So up to squiggles. Again, this is all very low level. This much is very low level theory. Just you take the kinetic term of higher dimensional potential fields that we have in string theory and integrating them around some cycle in the internal dimensions gives you a scalar field axion. And their kinetic term comes from the usual field strength in higher dimensions. Okay, so you can easily reduce that. That gives you an expression which, as you can see from the field strength kinetic term, has a bunch of inverse metric components. And you translate that into the period of the canonically normalized axion A, the period being F, and you can see that it goes inversely with the size. It also goes proportional to the coupling, and so the weaker the coupling of this higher dimensional gauge field, the smaller the period.
So the better control you have, the smaller the period is I think a fair way to say this point. Oops. Okay, so, but generically the potential does depend directly on the axion fields in a way that's completely consistent with gauge symmetry. So if you open Joe's book, you find these generalized fluxes, which are basically Stueckelberg-like combinations of fluxes and potential fields, which include, sufficient nonlinear transformations of the potential fields depending on the fluxes, so that the action is gauge invariant. And again, the axions come from integrating some higher dimensional potential fields over some cycle, like the universal B field that couples to a string leads to an axion that I'll call little b. And you can see there it's got a direct dependence and not a cosine-like potential for but for completely gauge invariant from this completely gauge invariant term. So when you reduce, you get from the field strengths, you get flux quanta, and from the big B's and C's here, you get the scalar field axions. So again, this is like a generalization of a Stueckelberg coupling that we're used to from symmetry breaking. But one kind of interesting question here is there a corresponding unbroken phase? If you do, say, start in the 10-dimensional string theories, write down those terms, their coefficients aren't obtained explicitly as the VEV of some symmetry breaking field. These terms are there. They give gauge invariant combinations, as I keep saying, but not as a result of a sort of traditional Higgs, abelian Higgs model type symmetry breaking process. Anyway, for inflation, this is the source of the direct dependence on the axion fields that there is in the potential. They do couple to the size and shape of the extra dimensions. Roughly speaking, these potentials have two different kinds of stabilization structures. The sort of nice, fun one is the one which you use fluxes to stabilize, where you have sort of two dual cycles in the extra dimensions, and magnetic fluxes on one cycle push out on that. If you fix the volume on the dual cycle, magnetic fluxes on it push out, and so there's a x plus 1 over x type potential that balances those. And what basically happens generically in the space of fluxes and axions is that, again, the field strengths turn into flux quantum numbers, the potentials turn into axions, and they can help stabilize moduli such as this ratio of scales L1 and L2 that I wrote here. And here you see just the dumbest version of this flattening effect I mentioned earlier, a little bit more faithfully to the ingredients we have in string theory, where such a flux stabilization with one of the fluxes really being this generalized flux, B times a quantum number Q, stabilizes this particular modulus in a way that depends on the axion. And that leads to a potential that's flatter than the naive quadratic that you would have here. Okay, so that's that. And so it gives a lower tensor contribution for that reason. There's also this feature of string compactifications that they go to zero potential at weak coupling and large radius, either from above or from below. The ADS version that people like to talk about is a two-term like this. De Sitter requires an uplift at least of this complexity. And this metastable minimum is less robust against large field variations in the coefficients. So that has to be taken into account in explicit examples. Okay, so you find this kind of pattern. And then there are contributions to the spectrum of the theory that depend on the axion, which undergo their own monodromy and come back to themselves as you go once around the putative cycle. B goes to B plus 2 pi. And so there are all sorts of periodic effects that modulate the physics, but which respect a discrete shift symmetry left over from the original symmetry. Okay, so this is kind of the pattern that comes out of that.
What's the scale mu there in that?
Yeah, so mu is analogous to the m squared of the m squared phi squared model. it's an arbitrary parameter. It can be naturally small. It can be an exponential effect if you want to model build in that way, as we have. But it's basically fit to the data. It's fit to the amplitude. Well, you fit two parameters to the number of e-foldings and the amplitude of the power spectrum, and then you get predictions for R and for the tilt. And that remains true here. You also get highly model-dependent predictions for oscillatory features as well. And that's a lot of what remains to do. Okay, so I already sort of said this about symmetry. One thing I like about this subject is the way that, some structures in quantum gravity do connect to the observables and potentially to the observations. So the symmetry here, it starts out as related to gauge symmetry in higher dimensions. There's a periodicity that survives all of the instanton corrections. But there are couplings to other scalar fields which really have to be taken into account and are not automatically protected by symmetry. But then once you do that, the model is on the same footing as, say, the m² phi² model. It's radiatively stable for reasons of its approximate shift symmetry. Okay, so that's kind of the general picture. Okay, so I was saying there are all these data constraints that are coming fast and furious. Already, I've been trying to say that Planck discovered a new parameter as it is. Just we don't know what the parameter is, but it discovered some new parameter. For theory, I think it's very interesting to ask whether there are theoretical constraints that we can, really compare to the data constraints eventually when we understand things more systematically. So there's this mechanism which we understand, well enough. There are examples which appear as dots on this plot. But what is the general story? From the low energy point of view, people have made a lot of progress, again with some input from the top down, of really just characterizing theorems about signatures that go along with single versus multi fields, things like that. And it would be nice to be able to do some of that from the top down as well, at least within particular mechanisms. Okay, so there's some stuff going on the archive lately that I tried to catch up with, although I'm not working on it, which I'll cover next, which is this potential connection between the so-called weak gravity conjecture and multi-field natural inflation. So natural inflation is an older idea where you take traditional axions, which just have a sinusoidal potential, and use the nice symmetry properties of axions to get inflation. So it kind of has this swath here, and it's also gotten disfavored by the data. But anyway, it's interesting, very interesting to study in itself. And there's a possibility that people are pursuing that constraints just from theory could limit this, which would be particularly interesting if that is also the direction the data goes. However, I think we should be very, very careful before drawing such conclusions. So I'll cover that first and then see what else I can say. Okay, so there's a bunch of groups working on this right now. Goes back to sort of a Harvard paper in 2006, and recent work by Rudelius, among others, I guess. There's a Cornell group. I spent some time talking to Liam McAllister and Thomas and Cody about this by Skype to try and catch up to what the current statements are. There's a group at Michigan, at Maryland, and some others. Okay, so I don't think this is the time to really describe this so-called weak gravity conjecture in full detail, but I want to kind of give the ideas as I understand it, and then why those ideas connect to this question, this specific question about axion, or about natural inflation, multiple field versions of natural inflation. So, okay, so the sort of rough ideas are quantum gravity, excludes global symmetries. There are arguments from black hole physics for that, which I think we all know. So the idea is kind of intuitively, if you take a gauge coupling and send it to zero, there should be some, there should be some problems, and problems should hit you as you try and do that. I guess a related idea is that to avoid remnants, you want black holes to be able to dissociate into ordinary charges, according to this idea. And so you are led to make some kind of conjecture involving the spectrum of charges and masses, saying that the charge-to-mass ratio for some class of particles needs to be bigger than something, so they are repulsive and they don't form bound states that would be remnants. Okay. So, it'd be really fascinating if that had implications for some totally different subject, meaning inflationary cosmology. And here's where the connection would come from. So the basic idea is, if the Q over M, if you think in string theory language just as a crutch, you can T-dualize, or you just think in different dimensionalities in with or without string theory. Something that's an instanton in one setup can behave like a particle in a different setup. And so if you use that kind of relationship, Q over M becomes M Planck over the period F times the instanton action. So the instanton action is like the mass, and M Planck over F is like the charge. Right. Okay, so, and the instanton would be suppressed by this kind of factor. Okay. So, and what these people are grappling with, as I understand it, is which particles or instantons should one apply this idea to if one is going to do so. Because, if you include multi-instantons, their F is effectively, becomes smaller and smaller. So if that's all you need, then you don't really get an important constraint, especially since multiple instanton effects tend to be, suppressed by more and more powers of their exponential suppression. And so you just develop short-range wiggles on the potential, which are perfectly consistent with inflation. So in order to get a serious constraint from this kind of thing, you need, it seems, a particularly strong form of the weak gravity conjecture. And this is what these groups are discussing. They draw pictures like this in some higher dimensional charge space, where Q over M equals 1 is this circle, and find that, for example, if you allow there to be just a finite number of remnants but not an infinite number, then it gives, doesn't give any overarching constraints. It might limit the models a little bit, but it doesn't, remove this entire class. On the other hand, there is a stronger form than the original paper that's being discussed, which would actually include the whole class. And so if there's good motivation, and I'm saying if because I'm not particularly advocating this, but if there is good motivation for this kind of weak gravity conjecture, then it might have some implications. But it seems like it requires a strong form. And again, I personally, my guess is this class will be fine, theoretically, even though it may be disfavored. Also, none of this applies for the case where you incorporate this direct dependence on the axion that I'm talking about, simply because the whole point there is it doesn't matter what F is. F can be as small as you want, and the large field doesn't come from that. Okay, any questions about that? Yeah.
So when you mentioned the arrow, well, when you talked about the arrow on the previous page, you said something to the effect of in the context of string theory, but is there any other way to understand that arrow other than T-duality?
Well, I stopped myself when I was saying it just because I guess you could think about field theories in different dimensions, as we did back in the 90s, and think about, field configurations which are instantons in some dimension but become particles in higher dimensions. That doesn't really require string theory per se.
So you're allowing it to be more generic, but the crispest.
Well, I think
case.
in fact, I think this discussion is most interesting if we decouple it from string theory. In string theory, we just try and check, do the instantons ruin inflation or don't they? But if you want a more broad, principled, way of just eliminating this entire class of models, you would want to
You would want to decouple this from string theory. I'm just wondering if there's actually a concrete case where it's known how to relate the charged particles to the axions, except via T-duality.
Oh,
I totally agree with the motivation. I'm
yeah,
just curious if there's an example.
I don't know.
Okay.
I think the closest I know are just higher dimensional examples, like if the axion comes from some winding line, or if the axion comes from some Wilson line, then the charged particles under the gauge field can have rolled-line instantons around the extra dimension.
Okay.
And then their mass, which can be constrained by weak gravity, is then also tied to the action of the instanton.
Right. You do. Yeah. Even the sort of bottom-up people are led to add dimensions to talk about this, but you can do that without adopting full-fledged string theory if you know what you think about it.
That makes sense.
Something I've never understood about these weak gravity arguments is that I never understood the weak gravity conjecture to be more than an order of magnitude constraint, because there are things in the only real arguments I understand about it, you have to know things about the endpoint of Hawking decay of black holes in order to get, real constraints.
Yeah.
And so I never understood why any of this should be taken to mean that you couldn't have, 10 M Planck or 20 M Planck.
No, I mean the conjecture Q over M, the number on the other side of that is 1.
I know it's said to be 1, but what's the real argument for that?
No, whether Q over M is bigger or smaller than 1 makes a qualitative difference in whether extremal Rice-Nordstrom black holes can decay. It's true that the argument about whether having completely stable extremal Rice-Nordstrom black holes is a problem, that is not very clear.
Okay, good.
But once you say it's a problem, then the number 1 comes in.
Okay, but there's an argument that comes from the covariant entropy bound. Okay?
Yeah.
And that argument is a lot more robust if you believe the covariant entropy bound than just are extremal Rice-Nordstrom black holes a problem. And that argument, I don't see anything that has more than order of magnitude implications. I mean, maybe someone could explain to me what the crisp argument is for a 1.
So Ben, even from the perspective you gave, there's this distinction between whether you allow a finite number of remnants versus, only being concerned if it is an infinite number.
But either way, Q over M bigger than 1 is the relevant relevant criterion.
Yeah, but I'm saying for this application, it's really much less powerful if you allow a finite number, and it's just a thing about these charge vectors. It constrains the models in some way, but it does not eliminate them. Whereas I gather from Liam that if you wanted to insist that all black holes decay, the implications of that for this are not yet sorted out. So that could be interesting. Was there a question?
Yeah, so is there an independent argument without invoking the big gravity conjecture and stated it from Q over M just for M Planck or F?
Well, okay, yeah, maybe I didn't make it. I should have backed up a little bit. So I explained how, despite the order 1 squiggles, as Tom and others noticed early on, the more control you have for a single axion, just with a sinusoidal potential, the smaller f gets. But when you start having multiple axions, you just do all the linear algebra. You have, some matrix inside the cosine. You have a sum over terms. You can have kinetic mixing, and if you put all that in, it's freer. And there was a paper by Kim, Nilles, and Peloso, which did what's called aligned natural inflation with just 2, and there you can kind of make a tune to get an alignment that causes a large f. But now people are doing these nice statistical studies of large numbers of fields, and so that's part of where this is coming from. But it's also fair to say that if you really wanted to do that, because of the many fields involved, it's prohibitively difficult to really do it explicitly in some example. I mean, that's, we can plausibly do that with these single field things, but if you're trying to be extremely general, even though I said earlier to Jim that you just calculated, that's not really practical. So yeah. It would be great if some general principle had such an implication. It's just we have to be careful. Yeah.
Just as a comment, I mean, when I've looked at this stuff, it seems to be there's a bit of a fetish for showing that you can get arbitrarily large numbers of E-folds, or whether you can or can't based on the gravity conjecture. Frankly, if that number was bounded, I think that would be great. I
mean, once you fix, I should say, we're talking about real observations here, so we can, just fix the amplitude, and then nobody thinks you can get an infinite number of E-folds. Yeah. The potential just goes up to the scale of the moduli potential or whatever, and then you shut up about it. But it's just, so. Okay, so I don't really need to go through this too much, but we're also looking at this kind of question in axion monodromy, where we just want to know. We're being kind of perverse. So the first models landed in here, and the question is kind of, was that an accident? Let's try and push the theory way far away from there and see if it'll do that, or if instead it pushes back, either through the flattening or whatever. So we're not done with that, but there are some interesting results in progress. So let's just try to use this structure, which was giving this kind of pattern, and see if we can push the theory to ridiculously, extreme places. And well, within the critical dimension, that doesn't look possible. But I want to be intellectually honest, since I always go on about d greater than 10, I have to do it. I have to do it generally, and there's a danger that it could build up, huge powers. So these generalized field strengths, according to symmetries, could be, this general with high powers of the direct dependence of the axion. However, there are tons of fields that would back react. So the question is, start high, but low. Where does it end up? Okay, so I don't know the full answer to that, but I would like to. And one thing that has been done by Guy Garari is generalizing one of the first examples of this, which was not a traditional axion, but a twisted torus. So you take a Mill manifold, you have a torus, which evolves along some third direction to an SL2Z equivalent. And that defined as a manifold where if you put a brane or a flux in there and move around, it just doesn't come back to itself. Okay, so that was actually the first thing that clued us into this mechanism. And Guy has generalized it to all dimensions. And it's a fun geometric exercise where you generalize this, like I say, with arbitrary transformations of the torus in any dimension. And he finds in this class P ends up, the final power does end up less than 2, but that he can, putatively fill it up pretty finely. I don't think I really have time to go through the details. And we've been doing this also with the original generalized field strength terms, and for various reasons have not yet succeeded in pushing it to parametrically large P, but we don't have a no-go theorem either, so we're still trying to do this.
What do you mean by extreme topology? Large Hodge numbers? Or?
Yeah, that's all I mean. I don't mean anything. I think this is also generic, just like D is, so I have to be principled about allowing for that. And so yeah, I'm quite interested in whether it was an accident that we landed in that region. Okay, so just briefly, if people want, or I can stop at any time, there are some fun opportunities for phenomenology in the current data, which is to do with these additional structures that can appear both in the power spectrum and the non-Gaussianities. So again, I should emphasize, of course, the data is now in, and the big picture is it favors lambda CDM very nicely with a reduced chi-squared of something like 1.03 or 4. However, if you multiply that by the 2,000 modes that we have, there's still room for some structure in there. An improvement of fit could be as big as delta chi-squared of 80 based on this, if you knew what was in there, if anything is. Partly because of that, and partly because of these theoretical motivations, there's a lot of ongoing work on such structures. Okay, so I don't need to go on about this. This is, again, just one of the Planck slides on the kind of things that they have looked for. There's no detection at the moment. For these oscillations I was talking about, they're instanton effects. They can easily be tiny, but still worth looking for. There are some anomalies in the data, as you would expect, because they search for all sorts of things. One of them that I'm kind of intrigued by, which they also comment on, is a multi-frequency oscillatory feature in the non-Gaussianity, which, according to their analysis, not only survives but is enhanced with polarization and grows to over 3 sigma.
I'm sorry, but I guess I thought I had heard there was no sign of any non-Gaussianity.
So this is not a discovery of anything, but it's there as a 3 sigma anomaly.
So how long has that been around? I mean, I'm just curious why I never heard about it before.
Well, it's in the Planck papers. I can show you.
They kind of buried it.
Yeah, it's funny. I can show you where it is if you want. It's part of the reason they buried it. First of all, they do a huge amount and it's still ongoing. Part of the reason is polarization is still being analyzed for all sorts of systematics. I shouldn't say all sorts. For systematics that they understand, they still need. I mean, some they say they know about and they want to get out of the polarization data before they release that part of it. So all of the statements of this kind about these kind of interesting sort of weak residual signatures are somewhat on hold because of that. So that's probably the most accurate response. And you can, I can show you the place in the paper where they remark on this. And they do remark on this as an interesting hint. And when, could it be from, some more elaborate thing that puts it all together? Well, so here's an idea for that, which we're just exploring in the spirit of using the data for as much as we can. And in fact, if you take these oscillatory contributions that I was mentioning to be, in the regime where they're actually, most likely to be detectable, that actually takes you toward another regime of this kind of mechanism away from, the simplest slow roll regime to something where these repeated events would include the possibility of particle or string production every so often. And that scenario we analyzed previously in a kind of continuum limit where we just washed out the oscillations. It leads in that approximation to something with equilateral non-Gaussianity. And so our plan is to back away from the continuum limit, incorporate the oscillations, and see if it could potentially improve the significance of that.
This is the time dependence of the inflaton field creating particles?
Yeah. So again, just like the potential depends directly on the axion, so do a bunch of sectors of wrapped objects. So those things are, coming back around every period. In the slow roll regime, they lead to these tiny oscillatory features. If you make them larger, they can have a much bigger effect on the evolution to the extent that they can give something that's more, where you can inflate on the steep part of the potential, and that results in significant equilateral non-Gaussianity. So we're wondering if there's some regime in the middle that would put together those elements of this thing. I'm not, I'm doing this not, we won't fool ourselves. Either it'll improve the significance or it won't, and that'll be that. But it seems worth playing with. Also, if you look at the frequencies that poke out in the power spectrum and the ones in the non-Gaussianity, there's a common one. To see that, you have to take a log of one of their numbers and notice that it's the same as another of their numbers. And again, I'm not.
Could you say just a word about what it is in the data they're seeing? They correlate the 2-point function against the 3-point function?
Oh, they are talking about doing that. Oh, another thing to say about this kind of game is that I'll get to what you're asking, but when I say ongoing, they haven't really done the 3-point function through most of the frequency range because they know how and it's going to happen, but they've only sort of done that over a small range of frequencies so far. But the plan is to finish that and do a combined analysis between the 3-point and 2-point. Is that what you're asking?
Well, that's part of it. What is it that they actually noticed that was tantalizing?
Oh, this thing. Okay. So this is. So it puts a lot of things together. So you can roll your eyes as you wish. So log space oscillations. That's the thing we expect from these cosine of phi or f sort of thing.
And that's in the power spectrum.
But that's in the 2-point.
No. This whole thing is a non-Gaussianity thing.
So they look at a 3-point function and see an oscillation?
Yeah, they do. What they did is they to their credit, in my opinion, did both. The usual 3, the equilateral, local block by themselves, and they did oscillations with nothing else. But they also did oscillations on top of equilateral and flattened and so on. It's that with multiple frequencies apparently survives. Look elsewhere, and gets enhanced with polarization.
So as a template for the 3-point function, they added some oscillations as a function of L, and then that turned out to be significant.
Well, nobody's saying it's significant.
Sorry,
it's 3 sigma. That's this thing that I'm talking about. Yeah. So
it doesn't show up in the 2-point function, but it does show up in the 3-point function.
Yeah, in the 2-point function, these are the best fit frequencies. They poke out relative to other things, but it's perfect. Statistically, you expect that, and there's nothing. There's nothing. However, I don't think anybody's done a multi-frequency check in the power spectrum, so we might do that. But anyway, that's. This is one of those things where you don't want to make a big deal about it, but I don't feel totally comfortable dropping it either because and I think we do have some ideas for how to.
I'm not sure I understood that. Why would something show up in the 3-point function and not the 2-point function?
That's exactly, theoretically, that's a great question. What we have in both really is bounds. Okay, so the question is, should it have poked out further in the power spectrum? But to make that comparison, first of all, we need to do the same thing. We need to do a multi-frequency. But you're absolutely right. That's the kind of question that we're asking ourselves. In this trapped inflation, it was a really fun analysis of just the perturbations because they are not dominated by the usual source of perturbations, the vacuum fluctuations. They're sourced by the particles that are produced in a way. And so there are different contributions that come in both the power spectrum and the 3-point function. And so we want to do more mapping out of what contributes in what regimes, and indeed the ratio of the power spectrum to the non-Gaussianity is a big part of that. Sorry, I can actually. I guess I don't really need to do this, but if you want, I can show you. There are words about this in their paper because. Okay, it's buried in section 8.3. Blah 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 blah. Multi-peak equilateral. These interesting results reflecting blah blah blah. Yeah, so this is the thing I was saying to you, Steve. They have not been able to go up in frequency as much as they will soon. It remains a high priority to investigate this further. So that's true. However, it's it is putting a bunch of things together, so it could just be little things adding up.
You want to show your conclusions?
Okay. Yeah. Sorry. I don't really need to because. Sorry. Oh crap! This isn't even the right file. Never mind. Sorry. never mind. My conclusions are.
Okay, well,
my conclusions are sort of obvious, I hope. Sorry, I can find it. If you want, I apologize. Okay. I was going to give my 2 cents about de Sitter holography, but I don't think I need to do that here. Yeah, so here are the conclusions.
all right.
You gave a nice survey at the beginning of the polarization experiments that are coming online. Could you tell us the timeline at which we should expect reports of data?
I mean, the best I can do are those ones from Abby that I showed you. So, okay, so I can tell you what the people are saying. That's I can't tell you what actually is going to happen. Okay, so these guys have this in the can. They've been doing these 3 things: the joint analysis, putting bicep 3 in the field, and analyzing this data that they already have. So I think they're time limited, but this data exists. So I don't know when they're going to report on it, but they've collected it, so they're analyzing that. This is being taken now, but okay. And so bicep 3 is a new instrument, so it'll probably take a while to do that. Spider, they collected the data, it went well. They're projecting, 2 years to analyze this flight, which is only 2 frequencies, and then they'll do another flight, I guess, next year with an additional frequency, a higher frequency.
There were 2 other balloon-borne probes, if I remember correctly, EBEX and Piper. Have you heard anything about that?
Well, I thought EBEX had an issue. I don't really want to comment more on that or on Piper. I'm not trying to be totally comprehensive here. These are the ones I've been hearing most about. Yeah, but these guys say 2 years to analyze what they just collected. And it's pretty cool because they do this flight that takes like 20 days. That buys them 2 years worth from the ground. They had kind of an adventure recovering it, but they got it. I do recommend the YouTube. These guys, I don't know the timeline. I mean, I could find out more, but it's all instant gratification for us.
It's like waiting for Christmas.
Yeah, I agree.
I see that there are a lot of potentials that could fit the data that you can produce, and we've got one. Is there any sense in what the statistics for the possible potentials that string theory would provide?
Yeah, that's a nice question. I mean, or just in field theory with certain assumptions, you can try and do kind of a statistical analysis. So people are doing that. There's work by many groups, Easter, Pierce, and others. Again, Liam McAllister and others. So the first group I know has a nice statement about some kind of statistical distribution of tensor tilts in multiple field versions of phi to the p inflation. Another one I want to comment on is actually a student of mine did this is really not, again, one of these things that's simple but potentially important. So I mentioned this flattening business. If you do multiple field versions of things, they tend to redden the tilt just for sort of, again, very pedestrian reasons. If you take, say, some potential and then, let's say, one of these large field potentials, and you consider a multiple field version of it, in each direction you're living on closer to the origin and hence on a somewhat steeper part of the potential. And that's all that's going. That really is all there is to it. So it reddens it. And there's a nice paper by by Wenren, sort of doing a statistical analysis of that, and it kind of spreads these things out here. Has no effect on R, so that's still robust. Yeah, I like that direction. I think when it comes to the string landscape, it's very, very tricky because there are structural things there that you have to respect if you want to, if that's your goal. Things like there's no hard cosmological constant. Things like axion periods seem to be limited. Those things have huge implications, even though it's also true there are lots of solutions. And so if you just do a statistical analysis without enough of the structure incorporated, I find that not very compelling, and so it's a tough game, but I like the question.
More of a comment. There is a way that, for the axion case, that weak gravity can come in. I don't think it actually is a big deal. But in most of these models, there can be domain walls, which induce transitions between the branches of your monodromy potential. So those domain walls can be charged, and there's an upper bound on their tension. Now, if you just look at m squared phi squared, just as a benchmark, even though it's ruled out, if I just naively put the one in that you're talking about, the upper bound and the tension, there's a factor of 5 between that and the lower bound set by making the domain nomenclature have an action of over 1. Now, that factor of 5 gets raised to the 4th power, and the standard sort of time formula for bubble nucleation, so it's not a huge deal. And also, if there's any flattening, the energy difference between the branches decreases, and that also.
Okay, good. Thank you. So here I emphasize instantons as a way to, as an effect that can reduce the period in some cosine. What you're saying is you can have other effects of instantons that that can take you between branches. Of course, you're always fighting do you just roll down or do you tunnel dichotomy, and that's why
so the action is to make sure that there isn't a rapid rate for tunneling.
Yeah, exactly.
That sort of gives you the lower bound, and in m squared phi squared, in terms of energy scales, it's surprisingly tight. But the energy scale gets raised to the 12th power.
I mean, it must depend somewhat.
Action, so it's not a big deal.
Yeah. Okay. Yeah, I see what you're saying.
In your view, is there any viable top-down small field inflationary model?
Oh, I don't see why not. I mean, do you mean in the data? Sure.
No. In model.
Yeah, I was emphasizing these ones because they are the most sensitive, and this measurement is being made these days, right? But here's a possibly incomplete list of a bunch of them. I mean,
that one I thought whatever the alphabet soup one, I thought there were problems with its tilt. I thought if you.
No, well that there may well have been papers saying that, but it really depends on all these higher dimension operators and what they do, right? So, I mean, I'm just saying, these kinds of estimates say that if you got some such contribution wrong, you could, if you thought your tilt was wrong, you could probably shift it around with such a thing. And I'm not saying that that's explicitly understood, but are you saying?
I thought when Liam and his friends did surveys over, likely places to land on the inflection point, you very likely landed on the wrong side of the tilt.
Oh, you mean the blueness of it? Right. It's true that they did those studies, but
if you had another theory of how you enter or something.
There could be another theory of how you enter, and it also could be that even if statistically you're often in the blue region, well, to actually rule out the whole class, you would have to not have any examples that work, and I doubt they were saying that. I think, but I'm sorry, I haven't really thought about that scenario much lately. But I'm pretty sure it would be, in this business, just complete no-go theorems are very hard, as are, absolutely explicit constructions, and so we're kind of in the middle ground, but that's fine. Yeah?
It's a little unclear to me where this can go in the future, even given new data. say we get, 2 more measured numbers or something. Where is it going to place us in terms of confirming let's say, a string scenario behind what we're observing?
It's a serious test of a large field inflation mechanism. Such mechanisms really require control of quantum gravity. That's the invariant thing that I can say.
Okay.
You could ask, what if we don't see any of the smoking gun, residual signatures like these oscillations, and that's entirely possible, even if we do see R, right?
Right.
And then, of course, we won't know, the details of the mechanism. However, to me, it's a lot like the cosmological constant, which, it's a single number, but it immediately put theory way behind experiment, right? I mean, we're still trying to understand the framework for that, even though it is one number. And here, this would be one number, maybe a few, maybe more eventually. But since it's so UV sensitive, it really, and this is already been happening, it really motivates as much of a being as systematic as possible in theory. And so there's a lot to do. I mean, the value of it, like all the excitement that happened after the announcement, would be just as valid at any value of R. So the value of 0.2 really had nothing. I mean, it exacerbated. By the way, that value really would have been in tension with large field inflation in this kind, as we understand it, most simply because of the fact that it would have required some very special thing to happen at the beginning of inflation. It would have been exacerbating the so-called low L anomalies, and so that's in tension with the control of large field inflation that we have that goes off to large field range without using a symmetry principle, which would be violated by some sudden step or minimum in the potential. So in some ways, a detection at a lower value would be more in line with these kinds of mechanisms. But I'm saying, any value is just as exciting. So
one more question, maybe we should end after this one.
So there's been some recent work basically showing that there is a dependence on initial conditions. Namely, if you just assume non-boundary initial conditions, no interactions, you will end up in a non-boundary state. And also this in conjunction with the fact that you just need 2 e-foldings to get you from Planck scale basically to Hubble scale. Somehow suggests that there will be some sensitivity on ultraviolet completion of the theory in the initial data, in the initial conditions, in the initial state, the way you set it up.
So I didn't.
And the analysis that typically is done by you, I mean not just by you, but almost everybody, right? It's assuming floral inflation, which basically puts you to the attractor solution. And that's not necessarily the case. So the question is, do you think it's worth studying this?
I think the questions about it. I think the questions about initial conditions are fascinating. I understand the kind of thing you're alluding to, but I don't understand the details of any confident statement that anybody makes about, what's most probable or not from the point of view of initial conditions. It has, it depends on your measure for what happened before and all this stuff that I personally don't, know the answer to. The way I think about it is, again, very simple-minded. It's to get inflation going, as you know, you just need the other sources of stress energy. You need the potential energy to dominate, but what that really means is you need the other sources of stress energy to be a bit below it. You don't need to be dead in the bunch-Davies vacuum. You need some control factor of 10 or something. And, I'm willing to buy that, and I'm willing to apply that logic to the phenomenology of inflation in the same way I would to any other subject in physics where we don't explain the initial conditions that led to, this material that we work with or whatever. It's just it's a very interesting question, but it's a different question. So.
Yeah, but once you include interactions, Bunch Davis is not even a chapter, right? I mean, one should keep that in mind.
I'm not. You should tell me afterwards
Yeah,
what you mean by that. I don't understand that kind of.
All right, thank you.